Thanks a lot. Thanks for welcoming here and also for the nice introduction. It's a great pleasure to give you a short insight in our work. Empa, Joel Meso already introduced Empa as part of the ETH domain. We are focused on material science and technology. We're starting sometimes on the atomic level, with these graphene ribbons, for example, but we have scales going up to structures like bridges, buildings, or whatever. But usually it is always starting by material science, and out of that, we're developing components, technology, and systems. Today, again, for all the people who attended yesterday's meeting, I still talking about carbon. And why carbon and energy, as we heard before, I think these both elements are quite close together or have to be think together. Otherwise, we are not solving that great challenge of our time to reduce carbon in our atmosphere. To start with, um, my topic is atmospheric decarbonization. And also, to start with, let's have a look at the carbon emissions in 2018. This looks like when you do a resolution of zero point 0.1 to zero point 0.1 degree uh, resolution all over the world about specific carbon emissions. So there are measured data from NASA and just displayed. And what did you really observe? It's a problem not from the south. It's a problem of us. The greatest carbon emission you will observe in North America, Europe, India, and China. Even our countries like Switzerland and Japan, a little bit smaller, but they're still very highlighted there. And so it's our duty to solve that problem. Well, this is a snapshot. Let's have a look more on the time scale, what's happened with carbon in the atmosphere or on the planet. And this is a shows how carbon is evolving over time, the emission. But the interesting part on the graph is how carbon is filled in the natural reservoirs. For example, land sink. That means if this reservoir is full, it takes about decades to remove that carbon by land or the surface of the ocean. Or we look on the reservoir of the ocean. There, if the carbon has to be removed naturally, it takes decades to remove that. And last but not least, in the atmosphere, if this carbon has to be removed naturally, rocks, sediments, or whatever, there are hundreds of thousands of years to remove that. And this is the problem which nature not can solve to balance that out anymore, because with our technology, we filled up that carbon storage or that carbon reservoir too fast. And now we have to actually work against it. If we are not work or if we are not balancing these reservoirs again, because nature is not able to do that, in a recent time, which is for us as human being suitable, uh, we end up with climate warming, of course. This is happening right now. And also interesting what Joel Meso mentioned, Switzerland is facing even higher temperature as the global average. I'm not sure what is in Japan, if they are these countries also facing higher temperature as the global average. So Switzerland is affected more than the global average. So it's also our duty to work on that. This brings me to the challenge of Switzerland. This is the carbon emission from Switzerland, and you see the major area where carbon emission happens, and we are roughly on 22 million tons plus aviation. Uh, According to the Paris Agreement, this is always a bit treated separately because it's outside of the boundary where it happens. But if you include that, we have about 47 million tons carbon to actually reduce or to remove of our system. How we can do that? There's a great plan to do about 70% carbon emission can be reduced. What is remaining at the end are these hard to abate carbons from partly from industry, partly from agriculture, and of course this jet aviation or this kerosene. And we heard there are some solutions going there, but there's still some hard to abate emissions. So what can we do now with this hard to abate emissions? Whereas, as we heard before, we can do point capture, where when we have the source, where we can actually suck that in on the chimney, or we can do direct air capture. This is, of course, the most hard way to do it, because first you dilute that into the atmosphere and then you have to concentrate that back in order to collect the carbon again. What we started at Empa, but also with the other institutes in the ETH domain, it is called mining the atmosphere. And this is now something looking in the next chamber of scientific challenge. This one, we should do that straight away. This is to stop carbon emissions of today by integrating renewables. We have to do it faster and today, otherwise the reservoir getting even more filled up and it's getting even harder to do it. Our research right now focus on the next part, and it is called this mining the atmosphere, and it's all about the questions how we can remove that, how we can clean up that mess what we have done over the last 80 years. Well, if you want to have a scientific phrasal for that, of course we have that. It is called carbon capture, utilization, storage. Forget the storage. Of course, we have to store at the end something, but I think it is much smarter to do the utilization, to see the atmosphere as the new resource for building up uh, fantastic new materials. Here we are on material science again, but not from fossil fuels, but really from the sky. And this is also what we showcased at the Expo 2025 in Osaka, showcased how we can actually mine the atmosphere, how we can turn the collected CO2 emissions into valuable products or into concrete. There are three topics which I would like to introduce. First of all, carbon capture itself, why does it make sense? Second, what we can actually do with this collected carbon on concrete and on a other valuable product I will introduce. So I would like to start with the carbon capture. We have all heard about that, how it works. First of all, we have to do the renewables. That means we have to produce hydrogen by renewables. And then we have carbon dioxide, which we have to actually collect by direct air capture. We do material science on that, like silica aerogel, what I mentioned yesterday. It's a very strange material, it's very fantastic, but it's still inefficient. We are looking also in new materials to do that much better in order to do this carbon capture. But then it needs another another large amount of energy to the synthesis and producing synthetic methane. And then when we have the synthetic methane, we are not burning it. Even today, we heard about processes which are burning we are burning methane or part of it. What we can do is we go into a pyrolysis and split them up into hydrogen and black carbon. It is powder at the end, like a solid material. And the hydrogen, of course, can be used in industry for high temperature solutions. And the powder itself, the black carbon, can be used as a feedstock for all our materials. What we are also have to be assured at the end that the carbon which we are collecting ends up in powder and it is negative over the process. That means not generating carbon during that process again, which compensate that. So we have to be really look on the whole path that it really ends up as a negative carbon powder or black carbon. In order to do that, we do material science, but we are also installing demonstrators that we can do research or applied research and transformation to industry on real scale. We have the nest. It is actually a stapled quarter or like a stable neighborhood in real size, which stands for all the different usage, what you actually can observe in the urban areas. And out of that, or within it, there is the energy hub. And the energy hub is not only the energy itself, we're also integrating the carbon cycle completely. Everything in real size. So we have carbon capture, DAC from Climeworks. It's also a startup from ETH. And we have electrolyzers and close to that facility, a pyrolyzer. If we do that, we have the powder, what I mentioned. Now we can turn it into a valuable product. And the first thing what we want to do is put carbon into concrete. Why? This is the material which is most used in our urban areas. So the turnover is huge. 95% mass uh, is the material used by construction in urban areas. So there's a great chance to integrate that huge amount of carbon. And how we do that, we make pellets out of it and integrating that into the concrete. This is CO2 negative concrete. Why? If you have ordinary concrete, as you see there, and you integrate that carbon, you get to net zero. But if you go to a carbon which is already better cement like EPFL, Karen Scrivener, with this, now I have to say it the right way, limestone calcinated clay cement, LC3, you integrating that cement in the concrete, you're already negative on that. And what I brought with me is like this concrete. If you're interested, you can actually also touch it, scratch it, or whatever. It has nearly the same performance as an ordinary concrete. But the next field, what we're going to do is put carbon not as carbon, so carbon in a silicon carbide, and put that into the concrete. It is also CO2 negative, but interestingly, it has 30% higher performance than the ordinary concrete. So you have a high performing concrete, you can do less material for the same performance, but still CO2 negative. This is one way to do that. And of course, what we also do in practice now, we can put that in concrete, but we can also put that in asphalt. What we do is Zug, where is also the pyrolyzer located. We use that carbon of the pyrolyzers and bring that into the asphalt for bike lanes. So we have maybe next year, maybe in 1.5 years, we're actually building the first CO2 negative bike lanes in Switzerland. Last but not least, we can use also the carbon to do other valuable products. For example, using carbon fibers. Carbon fibers are high-performing fibers which can be used everywhere, in automotive, but also for high-strength application. So we can use that. We have also spin-off to do hangers out of such carbon with carbon fibers. And these hangers can now be used for bridges, not steel anymore, much lighter, much more performing. And we also received building awards for bridges in Germany for the first hanger on a bridge which are fully on carbon. But this is just half the story. What we also have to look, if we use that carbon, do it that we can recycle it. We have now a patent how we can actually dissolve that hanger, get rid of the epoxy, and get the fibers back to use that in the similar way as it was used originally. And that means we can close the cycle now also on the carbon flow. And of course, the epoxy has also to be recycled. These are really a glimpse of our research at Empa. If you are more interested in mining the atmosphere, this is the full concept. There's also a link. You find the literature on that. More than happy to discuss afterwards. Thanks a lot for your attention.